Okay, the goal of this tutorial will be to input our flow data and run our simulation. This will go significantly faster than the geometry, which, as we saw last time, it can take a significant effort to input your geometry. For steady flow analysis, though, the input of the flow data is relatively straightforward. And so once we get an answer, we'll briefly look at some results and try to discern whether those results are reasonable or not. So quickly going back, oops, that's not what I wanted to do. Back to our problem here. Again, we've got flow in a trapezoidal channel. We've already discerned that we expect to see an M2 profile for this discharge, 30 cubic meters per second, and we identified a control or a boundary condition here at the downstream end of the channel. Okay. So we will now input the flow data and see if this qualitative result is confirmed by our numerical solution with HEC-RAS. Okay, so again, we've already, this is the model we brought up before. You can see we're in the project example 5.2, and we have a geometry file loaded. This is what we created in the last tutorial, geometry 1. And if you click on the geometry editor, here you see where we left off last time. Okay, so the geometry file is in there, and we can exit the editor. Next thing we can do is edit our steady flow data or use the steady flow, edit steady flow data button. So that's what I'll hit there. They take you to the same place. And you're taken here to the steady flow data window. First thing it asks you to do is edit or enter the number of profiles. This is basically the number of flow rates that you want to analyze. So HEC-RAS has the ability to run multiple steady flow rates in your channel at once. For this tutorial, we only have our particular problem has one flow rate, so that's what we'll stick with here. In a later video, I will show you how to input a second one here, but it's as simple as simply changing the number 1. And if you come down here to your location and profile names, you can see here's our Big River Reach 1. This is our upstream boundary, River Station 1400, and then PF1. This stands for Profile 1. So they wanted, what is the flow rate here? And for this particular problem, it is 30 cubic meters per second. And notice when we enter it, it's also a little bit brown, much like the cross-section editor. We need to hit Apply Data, and it turns black. We're ready to go. The locations of flow data change. This is if your flow rate changes for some reason in your channel. For our single channel with single flow rate, we do not need to put anything in here, but we do need to address the reach boundary conditions. Again, we're solving an ordinary differential equation. We need a boundary condition. So let's click on the boundary conditions button, and it takes us to our boundary condition window. It asks you if you want to set the boundary for all profiles or just one at a time. Since we only have one profile, it doesn't matter. We'll set all. You can leave it at the default. And then it says available external boundary condition types. So these are all the different boundary conditions that could exist. One is a known water surface elevation. So for example, if your channel ends in a reservoir of a known water surface elevation, you can enter that. One is critical depth. Another is normal depth. The fourth type is a rating curve. So if for instance, at a USGS gauging station, you'll know the discharge based on water surface elevations. So if we click on this, you could enter the stage or water surface elevation and the corresponding flow rate. We don't have that kind of detailed information, so we won't be using that. In fact, if we go back to our sketch, we know that at the downstream boundary here, we expect flow depth to be critical. That's our boundary condition. So we can go here, we can set the downstream boundary and click critical depth. And notice downstream is critical. We don't have to enter anything for the upstream, and we can click OK. And in a later video, I will go over some of these other boundary conditions options. But this is all we need at this stage. So we can click OK. And we're ready to go now. We've entered our reach boundary condition. We've entered our flow rate. We go ahead and apply that boundary condition data. And now we want to save our flow data. So we go to Save Flow Data As. And again, notice it goes to our default project folder. Let's call this, much like geometry, let's call this flow 1. And click OK. Okay, and that's it. We've now entered our steady flow data, and we can exit the flow data editor. And we're ready now to move on to running our steady flow simulation. So again, you can click the running man, or you can go to the run steady flow analysis here. Let's click the running man. And this is the way HEC-RAS organizes a simulation. They call it a plan. So we can see here, you say, these are all a new plan. Let's save a plan. So, or we can say new plan, and we're going to call this plan, we'll call it plan 1. And we can click OK. And it's going to ask you, it says enter a short plan identifier. So this is just a shortcut. We can call it, say, P1, then that will make sense for that plan. And what a plan is, once we create here, now you see your short ID, is it's basically a combination of a geometry file and a steady flow file. So you're saying, I would like to run this flow through this geometry. And in this case, we've only created one geometry file and one flow file. So we only have one option. We'll expand on this in a later video, but this is all we need for now. And notice it asks one other thing, and that's to the flow regime. So if your flow is entirely subcritical, you can leave this here. If you expect it to be entirely supercritical, you can click here. If it is mixed, mixed means a mix of sub and supercritical, you can click there. If we go back to our sketch, this is why the sketch is so helpful. Notice I keep referring back to it. All of our flow is above the critical depth line, so we expect it to always be subcritical. So I'm going to leave it at the original default and say subcritical. And at this stage, I'm going to go ahead and save the plan again. We're ready to compute. So we're going to click the compute button. This is going to run our steady flow through our channel. So let's do it. Compute. It opens up the computation window, and you see it tells you the percentage complete, but this went quite fast. It's already done. And it tells you the profile. So that was, again, our discharge. And the simulation, there was only one, so it ran 1 of 1. And it gives you a little bit of info here. It's good for troubleshooting, but we won't have, I don't think we'll have any problems here. And notice it gives you the time, the computation summary of the time. And as you saw, these are all less than a second or so, so it went very quickly. All right, and we have now completed our first simulation in HEC-RAS. So it took a lot of time, but here we are, we're done. And we can hit close, and we can close our plan now. And notice our window is now pretty much complete. We've got our project name, our plan, which again was a combination of a geometry and a steady flow, which you see here, geometry file, steady flow file. And then unsteady flow, we're not doing that, so it's empty. And all of this shows the locations of where our files are. And so you can see a plan has an extension, file extension .p01, geometry .g01, and your flow is F01. So you can, when you see these in your folder, you'll know exactly what they are. Okay, so once you have a solution, it is now, you now have the responsibility as the hydraulic engineer who ran the simulation to evaluate your result and figure out whether it's good or not. Again, the computer only knows what you tell it to do. It's your responsibility to evaluate that solution and figure out whether it's reasonable or not. And this is where all the buttons here come in handy. These are all your visualization tools, or you can use the view drop-down window. But I like to just honestly work my way across. The first button here looks like a cross section, and if we click on it, sure enough, it's a cross section. And notice river station, so we're at the most upstream river station, 1400. And what does it show us here? The blue is the water, the dark blue is the water surface elevation, and then the green dotted line is our energy grade line. So that's the elevation of the energy grade line at that location. And you can see it here. Within the channel, there are red bank stations, and it's showing our Mannings. And again, if you can change the view, if you go to options, you can change variables and things like that. But the default is pretty good. And we can scroll. Let's go to our most downstream end, River Station 0, and have a look. We see all the same information. There's our energy grade line, our water surface. Notice this red cross, though, right here, the plus sign. This is the critical flow depth. And notice that it corresponds with our actual flow depth. So we are crossing through critical here at our downstream boundary, which is the boundary condition that we specified based on our qualitative sketch. So there really shouldn't be any surprises there. I just wanted to show you that it is doing exactly what we've told it to do. Now we can just scroll through others. So if we move up to the next river station at 100 meters, you see it here. Notice it calculated the critical depth again, and it found that it was subcritical. HEC-RAS will check if it thinks it's close to critical just to make sure that we shouldn't select a mixed analysis. But here it's subcritical. And if we go to 200, it stops showing critical depth because we're clearly subcritical in this regime. Okay, and we could continue to look at how the water surface changes in different cross sections. This is nice to spot check things, but it's very hard to see the whole channel by scrolling through individual cross sections. So I'm going to close this now and move on to the next one, which is the water surface profile plot. And you see it here. Very nice. Again, this looks like we looked at the cross-section version of this. Now we've added the water surface here. So we go from river station 0 to 1400, and you can see this very much looks like the qualitative M2 that we sketched. Notice the flow direction is mirrored. So here in our sketch, flow is moving left to right. In the HEC-RAS profile, it's moving right to left. Okay, but it's the same. It's clearly an M2 profile. And you can see where it's calculated critical depth just to check and make sure that we are in fact subcritical. And you can see the energy grade line here as well. If you don't like the energy grade line, again, you can take the variables out, or you could add different variables. The one thing, when I see this, the one thing I'm a little bit concerned about is notice we have this cross section and then the next one at 100. And we've got a straight line connecting it here. So we're not doing a really nice job of capturing that curvature, which I've sketched here so nicely. We're really doing, it's very discrete. We've got just basically straight line segments. And we'll see what the implication for that is in just a moment. But this is, honestly, this is the plot I usually look at first before the cross sections to get a general feel, and then I might click through the cross section plots. But right away, I'm not sure that I like what I see here, although in general, I'm happy because I've clearly got an M2 profile. Okay. Next plot is, this is just a general profile plot of any flow quantity of interest, and it defaults to velocity. So this is the velocity in the channel, and going from river station 0 to 1400, and you can see the velocity decreases quite dramatically and then continues to decrease over the channel. And this should make some sense if we bring up the profile plot next to it. We can see that the flow depth is increasing. So our flow area is increasing. So by continuity, velocity is going to decrease to compensate for that from Q equals VA as we move up the channel. We can look at, there's other standard plots. For instance, we could look at the flow area. And we could see the flow area, much like the water surface elevation, increases. And it increases quite a bit for the first 100 meters. And then less, so it kind of levels off as we approach the upper end of the channel. You could look at the change in top width, change in Froude number. Notice it goes from a Froude number of 1 and then decreases to quite a low Froude number here, around 0.4. And there's other standard plots as well that you can play around with if you'd like. Okay. The next plot, let's see, this is the rating curve. Since we're doing a steady flow, we won't have a computed rating curve. The next one of interest is, again, that 3D plot that we looked at earlier to check our geometry. Now, let's see what it looks like. Now we see a nice 3D plot with a water surface elevation, and this looks very cool, right? We can see our channel cross-section shapes and how the water surface is calculated relative to that. Now, just be aware, even though this is shown in fully 3D, HEC-RAS is a one-dimensional code. So at each of these cross-sections, there's a single velocity that's moving downstream. There's a single flow area. The water surface elevation is always going to be horizontal. Okay, it's really truly a 1D code. And you can see here moving from critical depth here, and there's the curvature in our M2, and then it levels off as we move around the channel. Okay, so this one can be fun. And again, you can play around with angles like so if you'd like to, make it, this looks maybe a little bit easier to see the curvature. You can play around with the different angles there. Okay, and you can also change, like for instance, if you don't like the labels there, you can remove the display river station if you'd like. I usually leave that in. It's nice to it's nice to be able to see those as you're moving as you're troubleshooting your solution and seeing how the solution is. All right, so we can close that. The next things that we will look at, again, this is for unsteady flow, you can tell from the hydrograph, is these two tables. The first is detailed output. This basically gives you a table of output for all your different river stations individually. So here we're at the upstream boundary, and you can see it gives your energy grade line elevation, water surface elevation, velocity head, slope of the energy grade line, all sorts of hydraulic quantities. One thing I'll bring your attention to is this max CHL depth. This is the maximum channel depth. This is the depth in the channel, which is basically the difference between the water surface elevation here and the minimum, the minimum channel elevation here. And again, remember, we set this as 1.4 when we did our geometry due to our channel slope. And you can see there's more, it also splits them up into channel and left and overbank quantities. But since we didn't have any flow in the floodplains, there's pretty much nothing there. Okay, and you can see various quantities, flow areas, things like that are all summarized. And we can scroll through all of our different cross sections. One thing I want to bring your attention to is at our downstream boundary, again, the flow depth is, let's see, what is the maximum channel depth? Is 1.03. That number may sound familiar. When we did the problem setup, we calculated critical depth, and that's in our MATLAB code. Let's take a look. Critical depth is 1.03. So we've simply confirmed HEC-RAS is basically solving the same equations that we are. That's kind of nice to see. The other thing that we could look at, and again, if we scroll up, we can see how these quantities change. Oh, did you notice that? There was some stuff down here, errors, warnings, and notes. When we went from River Station 0 to River Station 100, suddenly we got some warnings. And these warnings say the velocity head has changed by more than 0.5 feet. This may indicate the need for additional cross sections. And then there's a change in conveyance ratio and a change in energy loss. And notice this is all between River Station 0 and 1. Where does that occur on the channel? Let's have a look at our profile plot. That occurs here, right? And this is where I said I wasn't really happy with how we captured this change in the water surface. So, and these warnings tell us HEC-RAS is not happy either. It's a little bit concerned that we haven't captured the geometry here very well. And because of this, I'm not really happy with the solution. And in the next video, we're going to refine this model and get something that we're a lot happier with. But at this stage, the last thing that I wanted to bring to your attention with this table is if we go to our most upstream section, 1400, let's look at the flow depth here. The maximum channel depth is 1.75. That should also look familiar because if we go back to our computations that we ran to set up the problem, that's our normal depth. So I actually selected that length 1400 to make sure that we reached normal depth. And we could look actually to see when did we reach normal depth. Here at 1400 we've reached normal depth 1.75. If we go down to 1300, the next cross section downstream, we're also at 1.75. If we go to 1200, you can see it decreased to 1.74. So our flow depth reaches normal somewhere between 1200 and 1300 meters. So somewhere in this neighborhood upstream of our River Station 0. So this gives you an idea. Earlier in the semester when we said it takes a long distance for the forces to balance and achieve uniform flow. Now we know for this problem that long distance is over 1,200 meters or over 1.2 kilometers. So it's a fairly large distance, and you oftentimes would not see a prismatic channel over distances of a kilometer. Okay, so this is a useful table to get all of the individual values for your different cross sections. The last thing I'll bring to your attention is you can copy the data and headings to the clipboard so you can post it into Excel. And I'll demonstrate that in the next tutorial. It's very straightforward. Okay, the last table to show you is this summary table. This is a nice one as well because if you look at it, it basically summarizes everything for you at all your different river stations, going from upstream 1400 all the way to downstream 0 for our profile 1. Notice Q is constant. It's just telling us it's a steady flow. Our minimum channel elevation, this is the elevation of the bottom of the channel. The water surface elevation, the critical water surface. So what is critical depth? And notice here it calculated it. Same values we got with MATLAB. Energy grade line elevation. These are the same, by the way, just to be clear, these are the same values as are plotted here. So it's a tabular form, essentially, of this profile plot. Okay, energy grade line slope, velocity in the channel, flow area, top width, and Froude number. Okay, and again, this is a really nice quick summary to look through, and as with the others, you can copy the data with headings or data only to import into Excel or something like that. And there's a number of other, you could, for instance, if you didn't want to include your interpolated cross sections, you could take that out and you just have the original two that we imported. We created those. Okay, and there's some standard tables. Most of these are if you're doing particular types of problems like culverts, bridges, if you have ice cover, things like that. We don't have that in our problem, so we're totally fine. And this is really the last thing we need to look at. So in summary, what we've done today is we created our flow data. We used the Running Man. We ran it through a steady flow simulation. Then we analyzed our results. And our conclusion was, if we go back to our water surface profile, we're not really happy with this. And HEC-RAS isn't happy either, as it gave us these warnings. So our next video, we're going to refine our model and get a better solution. But we should take this opportunity to congratulate ourselves for running our first complete HEC-RAS simulation and getting something pretty close to what we expected to see. Okay, so on to the next one now.